And finally, we're looking at question 8, which is the very last question on the paper, which is looks like a bit of integration, maybe a bit of differentiation here. So given that e to the minus 2x equals 3, find the exact value of x. Okay, so we're doing e to the minus 2x equals 3, and we want to just rearrange this for x. So what we're going to do is do ln of both sides, which is going to get us that. Because ln is the inverse of a, we're going to get minus 2x equals ln 3. So x equals minus a half ln 3. Okay. Now use integration by parts to find x e to the minus 2x. Okay, so let's do that. Is that part B? Yeah. We're doing the integration of x e to the minus 2x dx over here. No, just an indefinite integral. And then this is a function multiplied by another function. So we're going to do integration by parts. And integration by parts looks like this. U dv dx, there should be a d there. The integration of u dv dx equals uv minus the integration of v du dx. So we have to be careful what we pick to be u and v for this. Now the best thing to do is pick u to be x, because when we differentiate it, because we're going to have to differentiate to put it in the integration by parts here, when we differentiate x we get 1, and that's going to help us out. I'm going to pick dv dx to be e to the minus 2x, and so when I integrate that I'm going to get e to the minus 2x, and it's going to have a coefficient in front of it of minus a half, because when I differentiate this I'm going to bring that minus 2 down, and that's what I'm going to end up with there. I'm going to end up with e to the minus 2x. So these are the things that I'm going to be putting into my integration by parts formula. Okay, so let's do it. We wanted to integrate x e to the minus 2x. Yeah, dx. And so that's going to be equal to uv. So that's minus 1/2 x e to the minus 2x minus the integration of v du dx. Well, du dx is just 1, so it's just the integration of minus 1/2 e to the minus 2x dx, which is a lot easier than the integration we had to start with. So this thing we were trying to work out here is now the same as minus 1/2 x e to the minus 2x. I'm going to take this coefficient out, so this is going to be plus 1/2 the integration of e to the minus 2x dx. This, and so when I do the integration of this, it's not such a bad thing to do. I've already done the integration of it once over here to get this over here, so I know what the integration of it is. So it's going to be plus 1/2. The integration of this is going to be minus 1/2 e to the minus 2x. And this has got a plus c on the end. So let's try and strum this all together. This is minus 1/2 x e to the minus 2x minus 1/4 e to the minus 2x plus c. Okay, I guess we can leave it like that. We could take a factor of e to the minus 2x out, but let's tidy it up a bit. Let's do that. So minus e to the minus 2x we'll take out. So inside the brackets we're going to get 1/2 x minus 1/4 I guess we could take half x out maybe as well, but plus a quarter, sorry. Let's see. Okay, and so that's the integration. So now we're on to the next bit. A curve has this equation here. Find the exact values of the coordinates of the stationary point of the curve. So stationary points, if you remember, it's going to be where the gradient is 0. So what we're going to do with this is we're going to differentiate it, and we're going to then put the differentiation equal to 0 and solve it so that we can find the coordinates of the stationary points. So let's have a go at this part, C part I. We're given the curve is what is it? Y equals e to the minus 2x plus 6x. Y equals e to the minus 2x plus 6x, and we want to find the coordinates of the stationary point. This is the stationary point of that. So let's differentiate it. The differentiation is the gradient, so this is going to be minus 2e to the minus 2x plus 6, and we want the gradient to be 0 because that's where the stationary point is. So let's put all this equal to 0, and then we're going to have to solve this. So this is going to be 2e to the minus 2x equals 6. So e to the minus 2x equals 3. And we've already solved a similar problem to this. In fact, we've solved exactly the same problem as this. E to the minus 2x equals 3. That's what we solved earlier. That's what we're solving now. So I know that the answer is x equals minus a half ln 3. And that is going to be the x-coordinate of the stationary point. Now, to find the y-coordinate of the stationary point, I'm just going to sub x back into here. So to find the y-coordinate, this is the x-coordinate. This is good. We want the y-coordinate now. So the y-coordinate is now going to be e to the minus 2 minus a half ln 3 plus 6 times this. So this is minus. But let's just write it like this: minus a half ln 3, and then we'll tidy it up now. Okay, so this is going to be y equals e to the ln 3, like that, because the minus and the minus cancel, and the 2 and the half cancel, and then we're going to get minus 3 ln 3. So the e and the ln are going to cancel here, so we're going to get y equals 3 minus 3 ln 3, or minus ln 9, so minus 3 ln 3. So the coordinates of the stationary point where the gradient was 0, it's got the x value of minus 1/2 ln 3, and the y value that we just worked out, 3 minus 3 ln 3. Okay. Come back up, see what the next question is. Determine the nature of the stationary point. So this is saying, is this a maximum or a minimum? We do this by differentiating the second time and seeing what the value of the second differentiation is at that x value. And if it's positive, if it's above 0, then it's going to be minimum. And if it's below 0, it's going to be a maximum. So we're trying to differentiate this. This. For a second time. So this was the first differentiation. We're going to differentiate a second time. So this is now 8 C pot 2. So we started off with y equals e to the minus 2x plus 6x, and we differentiated it once already, and to get minus 2 e to the minus 2x plus 6. We need the second differentiation to find the nature of the stationary point. So the second differentiation is going to be 4 because the power comes down, 4e to the minus 2x. And we want the value when x equals minus a half ln 3. So when x equals minus a half ln 3, we're going to put into that. So the d2y dx equals 4e to the minus 2 minus 1 half ln 3. I think we've already done something similar to this, but it's going to be 4. Minuses are going to cancel, the 2 is going to cancel again, so this is 4e to the ln 3. And the e and the ln obviously cancel, so we just get 4 times 3, which is 12. So the second differentiation is 12. 12 is greater than 0, therefore stationary point is minimum. And then we come to the very, very final part of the paper. The region R is bounded by the curve e minus 2x plus 6x, the x-axis, and the lines x equals 0 and x equals 1. Find the volume of the solid formed when R is rotated through 2 pi radians about the x-axis. So this is a volume of revolution. Let's just move down a little bit. So this is C part 3. So the curve we're looking at is the same curve from before, e minus 2x plus 6x. And we're looking at the volume form between 0 and 1, so I don't know, something. Imagine this curve has been rotated through something like that. We're trying to find that volume anyway. So the volume is going to be pi multiplied by the integration of y squared between 0 and 1. Okay. This is going to tell us the volume of that that shape there, or the shape that's formed. Y in this case is e to the minus 2x plus 6x squared. So we're going to say that the volume is pi 10 e to the minus 2x plus 6x all squared dx. Okay, so we're going to have to multiply out this here. So the volume equals pi times, keep the limits like that. So we're going to end up with e to the minus 4x, I'm going to multiply this out, plus 12x e to the minus 2x, plus 36x squared. Oh, just fit that dx on the end there. And this is we can integrate this now. So it's going to be pi. This is going to go to e to the minus 4x, but I'm going to have to put a minus quarter in front of it. This one here, when I integrate this, is going to go to e to the minus 2x, but I'm going to have to put a minus a half in front of that, so that's going to go to minus 6x there, minus 3e to the minus 2x, and then this is going to go to plus, the power is going to go up, and I divide by the new power, so it's going to be 12x cubed. And we were integrating between 1 and 0 there. So I just go through all of this, and I put 1 in for x, and then I put 0 in for x, so I'm going to get minus a quarter e to the minus 4 minus 6 e to the minus 2 minus 3 e to the minus 2 plus 12. And then I'm going to take I'm going to be taking away whatever this is when I put 0 in. So that's going to mean that I'm going to be adding, when I put 0 into this e to the minus 4x is just going to be 1. So I'm going to be adding a quarter. Now, minus 6x e to the minus 2x, when I put 0 into that, that's going to disappear because this minus 6 times 0. So I'm going to be adding another 3 here for the e to the minus 3 e to the minus 2x. I'm going to put 0 into that, I'm going to get minus 3. But because I'm taking away, it's going to be a plus. And then I'm going to be taking away 0. So that's it. Okay. And I just need to stick this all together, I think, now. Yeah, so I'm going to get minus 1 quarter e to the minus 4. I've got minus 6 e to the minus 2, minus 3 e to the minus 2. So I'll stick those together into minus 9 e to the minus 2. I've got plus 12, plus 3, that's plus 15 and a quarter. 15 and a quarter there. And I think that's as good as we're getting. So that's the volume of the... how do I have to write this? Let's have a look. Giving you an answer to 3 significant figures. So we're going to whack this in a calculator now, all these e values and the pi, and should come out with 44.1 to 3 significant figures. So that's the volume of the shape formed when we rotate it.